Okay, in this question, you have taken a meter stick or, a big plank of length L, and you're forcing it to pivot a third of the way down the plank. So the first question is find the rotational inertia. So remember, you can't just say, what's the rotational inertia of this object? You have to say where you're going to choose to grab it and rotate it. So this is a trick I expect you to know. It does show up on the assessments. You're going to just treat this like you took two pieces of wood, an orange piece and a green piece, and you glued them together and you're pivoting them about the center. Okay, so we got the orange piece on the left and the green piece on the right. And the orange piece has a mass of m/3 and a length of L/3. And the green piece has a mass of 2/3 m and a length of 2/3 L. Right? This has 2/3 of the stuff, and this is 1/3. And for whatever reason, what confuses people is that they're not sure that you can just add rotational inertia. But the total rotational inertia is just the sum of the orange rotational inertia plus the green rotational inertia. Because you're just adding up, let's make this purple. You're adding up how far is this mass from the pivot? How far is this mass from the pivot? How far is this mass from the pivot? Rotational inertia is additive. So if you have different objects glued together, you just keep adding the rotational inertia. And again, people get confused about that. So I just want to make sure people know that that is okay. That's how you do it. Okay, so that you are given two formulas for rotational inertia of a meter stick. One is if it's pivoted about the center, that's, remember, the lowest rotational inertia you can get. So that's 1/12 ml². That's not what we have. It's not about the center. About the end, it's 1/3 ml², because you've pushed the mass farther away from the pivot. So what we have is two meter sticks, or two, they're not meter sticks, but two bars at the end, right? We're pretending like the orange is held at the end and the green is held at the end. So we're going to say 1/3. The mass is m/3 and the length is L/3. And we're going to square that. So that's for the orange. Plus 1/3, because that's in the formula. This mass is 2/3 m, and the length is 2/3 L. Okay, handy little trick. All right, let's start to reduce stuff. We've got an m and an L² in my numerator, and you have 1, 2, 3, 4, 3, so that's 9 times 9, or 81. And you got a 2 and 2 more 2s, so you have plus 8 ml² over 1, 2, 3, 4 3s, so over 81. So 1/81 plus 8/81 equals 9/81 ml², or divide both sides, like 9 goes into 81 9 times. So that is the rotational inertia of that if you grabbed the meter stick right here and made a pivot there. Okay, awesome. And this is where it gets tricky. Okay, the rod is then released from rest. That is generally a hint that it's energy, that they're telling you that there's no kinetic energy. And we'll look at the picture in a minute. Calculate the linear speed at the end of the rod when it goes from point A to point B. And then these hints are clearly mine. They don't show up in the AP. Okay, and then I guess I told you what omega is and what V is. All right, so I hope it makes sense that even though this thing is rotating, mass is still changing height. When you calculate UG, you need to calculate the UG of the center of mass. Okay, so hint, label your sea level. I think it makes sense to call the end of the rod sea level. Okay, and then this is where it gets tricky. So I recommend that you like make a little mark at the center of mass. Where is the center of mass? It is at, let's see what color. It is at the midpoint. So at point B, the center of mass is L over 2. That's like a 4. That's L over 2 above sea level. Okay, so a common mistake is for people to say that the height of the center of mass is 0, but that's the end of the rod. What you want is where is the center of mass, and that is L over 2 above sea level. Okay, and then where is the center of mass here? This one's a little bit tricky because the center of mass is clearly aligned with the pivot, and that is 2/3 L above sea level, because that's where the pivot is. Hopefully that makes sense. Down here, this is, L is the whole thing, but what's, where the pivot is 2/3 of the way away from the end of the rod, and so if the end of the rod's at sea level, that's where your center of mass started out. Okay, so at point A, we have MGH because the center of mass is above sea level. We could have kinetic energy, linear and rotational, but it starts at rest. So I don't want to waste space. At point B, you also have MGH, unless you set that point as sea level. Okay, which you could do, totally fine. I think it usually just makes more sense to call the lowest point sea level. Plus, if I had a LED at the center of mass, so as this rod is rotating, here's the center of mass. The center of mass will do this. Okay, hopefully that makes sense. It is only, and if it kept going around, it would make a circle. So the center of mass is not translating through space. It is only rotating. So we only have 1/2 I omega squared. We do not have 1/2 mv squared. Okay, and what's confusing, the reason people get this wrong is because it asks you for the linear speed. So they think I got to have a 1/2 mv squared as well. I love the LED trick. An LED at the center of mass is only would form a circle. Okay, so it only has 1/2 I omega squared, and then we'll figure out what the heck that linear speed is talking about. Okay, so the mass is just m, right? All of the mass behaves, it's at the center of mass. So this is just m, g, and the height above sea level is 2/3 L. All powered by gravity, right? That's all powered by gravity equals same m, same g, but L over 2 above sea level for the center of mass. Plus 1/2, and then that's why they had you find I omega squared. Okay, so again, all all powered by gravity. You got to be careful where the center of mass is, and not assume that it's at the sea level, and then it is only rotating because you got to nail through it, right? It's not rolling down a hill. It is forced to pivot, and so it's only rotating. Okay, so then let's see what happens. The mass cancels. That's nice. And you have 2/3 GL equals 1/2 GL plus L squared over 18 times omega squared. What are we looking for? We're looking for the linear speed, so let's find omega because that's at least a speed. All right, so let's subtract 1/2 GL from both sides. And then you need to find a common denominator. Okay, so the common denominator is 6. So you're going to have 4/6 GL minus 3/6 GL equals your stuff on the right. Okay, so that's just going to be GL over 6 equals L squared over 18 omega squared, and then some other stuff is going to cancel, right? The L will cancel, and 6 goes into 18 3 times. So omega squared equals 3. Oops, that's an L squared, so only one of the L's canceled. I still have an L there. Omega squared equals 3G over L. So omega equals the square root of 3G over L. Check your work. You know, omega should be in radians per second, and G is in meters per second squared, and then you're going to divide by another meter. So this is 1 over second squared, and then when you take the square root, you get 1 over second. And remember, a radian is just a ratio. Okay, so that is how quickly at that instant, because it's not constant, that means at that instant it is rotating at the square root of 3G over L. And that's what you're going to do in the rotating ruler lab. That's how fast it's rotating. What is tricky is that they didn't have you find that first, but they're saying, what's the linear speed at the end of the rod? So this is why on that animation you had all those colored dots that were on a turntable, and they should have said, instead of linear, they should have said tangential speed, because it's not really going in a line. I think if I were to queen of the world, I would make that tangential speed. So remember those dots on a penny on the turntable, if it flew off tangent, it would have a certain speed, meters per second, because from a bird's eye view, it is traveling in a line, but it is moving through space in meters per second, and it just happens to be going in a circle. Okay, so how do you find how fast those dots are going when you know how fast it's rotating? Sorry, I'm running out of space. Let me do this here. The formula that says the farther I am from the pivot, the faster I have to go, and the faster it's rotating, the faster I have to go. So V equals omega R is your tangential speed caused by being on an object that is rotating. Okay, that's the tricky part. All right, so what is omega? Omega is the square root of 3G over L. What is R? R is not the length of the meter stick. R is how far you are from the pivot. And so what you're going to do is you're going to have the photo gate measuring the meter stick as it goes through the photo gate. The end of the meter stick is 2/3 L away from the pivot, right? This is the point that we care about that is traveling through space. So it's not L, it is 2/3 L. R is how far away that point is from the pivot. Okay. You really should clean this up, meaning you got some, you got an L outside the square root and inside the square root and some numbers. So bring everything inside the square root. So we have 3G over L, and this is going to be 4/9 L squared. And then you can see things clean up a little bit. You still have a G. You can bring the L squared out of the square root. I'm sorry. No, you got an L squared over L. So L, let's put the L, let's cancel one of these with this. And let's cancel this 3 with 1 3. So it's 4/3 GL inside the square root. Okay, so that to me is more clean than this. Sorry, that handwriting is a little bit sloppy, but it's 4/3 GL. Okay, so that was tricky. I talked about the warnings. I won't rehash it because we're already at 15 minutes. Okay, that is a classic problem. So I hope that makes sense, but keep going over it until it does.